the one I wanted.
If it works for, yeah, I don't have very dim pictures. They're all black and white. Yeah.
Okay, well, why don't we go ahead and get started? It's a pleasure to introduce our guest lecturer today, Pentti Kanerva. Pentti was my mentor at one point, about 25 years ago, maybe 30 or so, quite a long time ago, at NASA Ames Research Center, and got me started in this field, actually. And the thing that kicked it all off for me was his book, a very influential book on sparse distributed memory. And did Fritz talk about this at all in the associative memory lectures? No? So it's another kind of associative memory model, okay? And it's a very elegant idea. And lots of people say this, including Douglas Hofstadter, who wrote one of the little kind of like blurbs about the book here, which I'll read to you. So it's according to Douglas Hofstadter. This book, because of its pristine mathematical beauty and its great clarity, excited me deeply when I read it, and I believe it will have the same effect on many others. Pentti Kanerva's model was a revelation for me. It was the very first piece of research I'd ever run across that made me feel like a glimpse the distant goal of understanding how the brain works as a whole. And so I have to say that this idea that Pentti is going to tell us about today, it builds on this sort of basic concept, but it's taking a different direction. And this idea of hyperdimensional computing, it's taken me a while to kind of absorb and understand it. But the more I do, the more I say the same thing that Hofstadter said about it. So it's very subtle. So thanks for doing this, Pentti.
Well, thank you, Bruno. Thanks, everybody. What I'm going to talk about today is I've had it on my mind for a long time. And I'm trying to get it off my mind and put it into yours. But it'll probably still be on my mind as well. So if any of you are interested in these things, talking with me, I'm here usually on Fridays. And I'd be glad to discuss things further. And if you want to actually do projects, I have...
Quick announcement.
Oh, I forgot.
So
Yeah.
we just finished grading your previous content. And they, so I know some students didn't pick up their graded versions of it, so we thought not to disrupt the flow of the class, we'll put them up on the table there towards the end of the class, and you can pick it up and thank you.
Anyway, so if any of you are interested in working on these kinds of things, I'd be glad to work with you. So you can keep that in mind. I come to this more from the computer science point of view than from neuroscience point of view, and so you will probably detect that. But my initial interest in computers really was when I heard that there are these electronic brains. The notion that there would be a brain that would be thinking, that really fascinated me, and it has been with me ever since I learned I would say in my teen years, and it became my thesis work, and then I've continued on that route. So for what I'm talking today, artificial intelligence in some sense has been around and motivated my thinking as well. And the idea that the brain is some kind of computer, it actually goes back over well, as far as we have it stored program computer. The first date I have here in 1943, I'm sure you have run across some of these ideas. And there's McCulloch, Pitts, Turing, McCarthy, Minsky, von Neumann, very, very well-known people in computer science, artificial intelligence, and mathematics. I particularly like von Neumann's little book, Computer and the Brain. Unfortunately, he was not able to continue the work. He was working on it as an invited lecturer, and it became posthumously published as a book, but he probably would have been working on some of these ideas further. And here, I think Rosenblatt may be the name originally associated with artificial neural nets, and then there's Feigenbaum and Feldman in sort of traditional symbolic artificial intelligence. But if you look at these, the last day that I put in my list, 1964, so all of this is more than 50 years ago, and yet neither symbolic AI or artificial neural networks have produced the kind of intelligence that these early pioneers were.
Gary Feldman?
This is not. I think he was in Southern California, but it's not.
Okay.
It's J. Yeah,
Okay.
I think it's J. Feldman actually,
Okay.
but it's not our Feldman. Yeah. So the thing is, in ordinary everyday life, we do things that really go beyond anything that computers do today, and something that we might want computers to do, but they really don't. Like, we recognize people and things in all kinds of conditions, and we learn skills, and we learn to cope in the world. This is also learning a language. This is all everyday thing for us. Proved to be very, very difficult for computers. And then there's something that I really like, this idea of dealing with concepts and meaning. And I have a lot more to say about meaning in this talk. And then we understand things. We understand what other people say. We empathize with others. All of these things are very human things, and they certainly are not something that we sort of do with computers, or wouldn't, at least today, you wouldn't expect to do with computers. So some of the things here is to notice. First of all, perception is very robust. The same thing never appears exactly the same on two occasions, and yet we identify, oh, that's that person, or hear the phone on sound on the telephone is that person. We can identify people from all kinds of cues, and although the stimulus is never exactly the same, and situations never occur identically on two occasions, and yet we identify, okay, this is the same situation, we do the same thing to cope with it. So these are very human abilities, and we would like to understand how human beings actually manage to do that. Then there's another thing to think about, the concepts, and I'll be talking about the concepts. And one thing is that concepts have some sort of metric, and I'll give an example. Well, here, first of all, like, we have words for concepts. They're sort of like labels. And when I say the word red or apple or red apple, you have some sort of image in your mind, and you can use that image to get an idea what I'm talking about. And then this metric means that some concepts we judge as being similar concepts, and some other concepts we judge as being dissimilar, like red and yellow. For some reason we think that they are similar concepts. I haven't said what a concept is other than, but that concepts are similar in our judgment. Or something like truth and red apple, somehow it feels like they are very dissimilar concepts. So in some sense, truth and red apple are far from each other, and red and yellow are close to each other in this space of concepts, a notion that we have in our heads. And another interesting thing is that if you take two concepts just at random, they are unrelated to each other, just like the red apple and whatever was on the previous page. And here's my example, like man and lake. They are very different from each other. We have no real reason to say that man is similar to lake in concept, but we can connect those concepts with very few intermediate concepts, like man. We can collect man and fisherman. They are close in this space, and fisherman and fish are close in this space, and fish and lake are close in this space of concepts. Another thing, man and plumber, they are sort of closed concepts, and plumber and water and lake. So we can relate unrelated concepts with very few intermediate links. That's one of the things that seems to be very peculiar about concepts. And then the intermediaries need not even be similar to each other, like plumber is not similar to fish. So how would we model such concepts? Here comes the first test. I have two concepts. One would be train, and then I'm going to compare train to two concepts, and you can judge which one is closer to train, which one is far. Okay, which one is closer to train, bus or salami? Interesting. Now, how many concepts can you get from bus from train to salami? Let's see.
You get served salami on a train.
Salami on train. All right.
That's really good.
Yeah.
Trains are only cylindricals or salami.
You can do that. I think there are very many ways. When I was writing a paper about this, the chain that came to my mind, well, there's a train, there's a locomotive, which means there's engine, it needs fuel. Fuel, well, that's food, and food is salami, and so there's a very natural way of forming these kinds. So the space, that means that if we want to model concept mathematically, we have to have a space where this kind of thing is true, that you have things are generally far from each other or unrelated, but between any two related things you would have unrelated things, you would have related things that are related to both. And that's where we come, why high dimensionality? Would that somehow be similar to how our concepts are, how we feel our concepts are related to one another? And the thing is that there are properties of high-dimensional spaces that actually are appropriate for dealing with concepts. And one of the things is how high-dimensional spaces are distributed, and I'll have examples of that. And then particularly how distances in high-dimensional space are distributed. And this is conveniently demonstrated with 10,000-bit binary words, but the things that I'm demonstrating are general properties of high-dimensional space. It doesn't have to be binary. Binary is just the simplest way for us to actually believe that this is the case. And so if you take the space of all 10,000-bit words, that means they will be, in all the points of the space, they would be 2 to 10,000 of them. So that's a pretty big number. You might think of them as 10,000-bit words or 10,000 dimensional binary vectors. And here I started writing up one, and I sort of got tired. And but if you try to write all of them down, there won't be enough paper in the world to do that. 2 to 10,000 is a big number. Okay, mathematically, if you think of these, they are corners of a high-dimensional or high-dimensional cube or hypercube. So here, instead of 10,000, I've done a cube in 3 dimensions. But you can see that the corners are labeled 0, 0, 0. You go in one direction, you get 1 bit, or you get another direction, and so the corners of the cube or the vertices of the cube would be labeled then by 2 to 10,000 binary numbers. So the picture would be pretty wild to try to draw. I mean, 3 is fine. I've very nice drawings of 4-dimensional hypercubes that I haven't even tried to do beyond that. Okay, the distance in this kind of binary space is easily measured by the number of places at which 2 binary words differ. And engineers like to call it the Hamming distance. Mathematicians call it L1 norm. And if you think of the Hamming distance or the L1 norm, it's the shortest, from one point to the other, the shortest path along the edges. And of course, in the 10,000 dimensional space, it's anywhere between 0 and 10,000. And since it is a cube, or the corners of the cube, every corner of a cube is exactly like every other corner. Even if the label is different, but other than that, is every corner is like every other corner. So in that sense, there is no concentration anywhere in space. If every point of the space is like every other point, there's no special point. However, if you look at the distances from one point to all the other points, they are highly concentrated. And the term that statisticians now use for that is a concentration of measuring the number of points at different distances, then they are concentrated at certain distance. When we're dealing with binary numbers, they are concentrated at half the number of dimensions. So the mean of all the distances is in the 10,000 dimensional space is 5,000, and if you use the binomial distribution, you see that, I mean, the distribution of the distances is a binomial, and its standard deviation is 50. So the standard deviation is only 1/100th of the mean. I've put it in the relative terms, so that if the mean is 0.5, standard deviation of 0.5, so the minimum distance is 0, mean distance is 0.5, and the maximum distance is 1. And this kind of binomial distribution is very closely approximated by the normal distribution. And here I have put two binomial distributions, one that looks like your normal bell curve, and of course this also is normal curve. This with 10,000, when the number of dimensions is 10,000, it's very highly peaked and concentrated at half the distance. So much so that you can go from 0 to 0.47, and that covers only a billionth of the space. And then this narrow region covers, beyond that point is billions, and so everything else is in that very narrow band, and that's what they mean by concentration of major. Just at the very almost all the points are at that distance 0.5. So I call these points here that, I mean, there are lots of points here too, because there are lots of points overall, but these I call that they are similar or correlated. And in this region they would be dissimilar, uncorrelated, or another way of saying that they are orthogonal or nearly orthogonal, and then opposite would be with binary numbers you have an equal number in the opposite direction. But I'm going to make no use of that property, that there's also the other direction where you have very few points. Okay, just to sort of summarize what was on the previous picture, a distance of 0.47 covers only billionth of the space. Distance half covers half, and actually from this concentration, it means that this kind of high-dimensional representation is very robust. You can have lots of errors. You can correct lots of errors, and still, if you find what was the can find, you still can identify what the correct or what the intended bit string bit pattern was, and that is one of the reasons. I mean, in an earlier slide, I said that perception is tolerant of variation. It would come from this property of high-dimensional space, that you can have some prototype and you can deviate from it considerably in terms of just physical bits, and you can still identify it with what you have stored before, what you have seen before. So that's one of the reasons why I liked high-dimensional spaces. And here I summarize that the same thing never appears the same on 2 occasions, and yet we can identify them. And here's another way of thinking of it mathematically. With 10,000-bit vectors, if you just guarantee on second occasion that you guarantee 10%, you get 10% are the same as in the previous occasion, and you assign the remaining 90% at random, you will be 0.45 distant from the original, but that is still close enough in probabilistic sense that it is highly correlated and probably is among the things that you have seen, it's probably the one that finds what has been seen before. So that actually, I mean, if you think that nearly half of the bits can be different, then you can still identify something as has been previously seen or previously stored. That's the very important property that we get from high-dimensional spaces. Yeah.
You said 10% match and 90% are assigned at random.
Random, yeah.
50-50. So
yes.
Roughly half of those will also.
Yeah, then half. Yeah, right. That's right. Exactly. Yeah. Then about the unrelated to intermediate concepts, your from train to salami example. It says that although the maser is concentrated, or all the points are concentrated about 0.5 away, there still is a huge number of points in between, and so you can connect with very few intermediate concepts, any two unrelated concepts. So that's another property of high-dimensional space to keep in mind and appreciate. Yeah. Did you have a question?
Yeah. How does the concentration scale with the dimension?
The picture.
Okay,
yeah, the picture showed that when they're 15-dimensional, it was like a bell curve, and then when it was 10,000 dimensional, the bell was just like it became a steeple. Okay, now, what kinds of principles can we draw from looking at brains? Yeah, you have a question there?
Yeah, so with the high dimensions, I mean, how do we discern anything at all in this space? If they're all like kind of equally close on average,
yeah.
Like how you end up doing recognition. Like how do you know that, if I can assign 90% of everything at random and still get the same answer?
Of course, if to recognize something, you have to have stored it someplace else, and it's among the things that you have stored. The one that matches best among the things that you have stored is very likely to.
But if all the distances are very close, you'd have to do that like perfectly, right? Or there's like a very large set of very similarly distant points.
You're saying it seems to make you too tolerant.
Right.
Yeah.
Yeah.
Like how do you end up defining anything in a space where everything is so concentrated and like equidistant to other close points?
At random, if you take points at random, then that's when you get but there are still lots of points that you don't you have to play with. Okay, so let's look at brains a little bit in terms of numbers. Number of neurons, well, I get somewhere an estimate of 40 billion, and number of synapses, 240 trillion. And just to get an idea of how big this number of synapses, what it means in terms of information capacity, and just assume that each synapse is worth 1 bit of information. That's all you need to assume. Then that would be 30 terabytes. And 30 terabytes translate to something like 30 million very thick books. And if you divide that by 100 years, that would mean 800 books per day for 100 years. So if you relate it to lifetime, in some sense it is as if you were able to absorb information at the rate of 800 books per day for lifetime. So that gives some idea of what the information capacity is in our brains. That we came to this room with 800 books worth of information. And very interesting thing to keep in mind. Another thing, if you look at neural circuits, the fan-ins and fan-outs. There are some where it's very small, like may have half a dozen inputs or outputs, but they can be up to 200,000. And on the average, if you just do the calculation for this, and on the average it'd be 6,000 inputs per neuron, 6,000 outputs per neuron. So if you think of those as circuits, the circuits, each circuit would have 6,000. Well, I like to use 10,000 in my examples, but 6,000 is close enough to 10,000 that we are talking of circuits where the number of inputs is of the order that I use in my examples here. And these kinds of things are meaningful to engineers, fan in and fan out, and I think that's a terminology they would use. I don't know if neuroscientists use terminology fan in and fan out, but okay. Now, so let's get some architectural principles from these numbers. First of all, the circuits are very large, and that's how it makes reasonable to talk about 10,000 bit words that each circuit can deal with. And there's a very massive memory. Remember that several hundred books a day. Another thing that you want in these things is that the encoding of information and the storage be separate. And this is one of the things where I feel right now when we have these deep learning nets, this is still violated, and so long as it is violated, I don't think we will have reasonable systems can learn lifetimes worth of information without sort of stepping on what is already there. So there are some really serious architectural constraints with the present systems, and I think those will be ironed out in time. Yeah.
Can you clarify what the terms encoding of information and memory storage mean, like the differences?
Okay. Memory storage is very much like what you have in random access memory in a computer. You put something in there and you have an address. You use that address to put some data in the memory, and a year later you want to be able to, if you get the same address, you want to be able to retrieve what you put in the memory. That's how RAM works. So long as you don't step on the location, don't reuse a memory location, this is true. And so here too the memory would have that function. It's a storage, and then the encoding will be shown in an example, and that's how you produce new representations from existing representations. That's what I mean by encoding. And it's very much like what happens in ordinary computer too. You have random access memory that stores information, and you have arithmetic logic unit that has the circuits that does computation. You give it two numbers, it gives you the sum, or you give it two numbers, if you give you the product, that's the encoding. That's a very important thing to sort of understand. That those are what they do, and they be different functions. And another thing is that there has to be. Oh, did you have a?
When you say we learn information fast, what is fast? Right?
What is?
On the previous slide, you had a sentence. Yeah, and it says large amount of information is learned fast.
Learn fast. You can learn a new fact by being exposed to it a couple of times, 3 times, 4 times.
But I mean, isn't there some kind of argument in there in the sense that I'm kind of primed to learn a new fact for like the first few years of my life when I'm just sitting around and looking at things, right?
Some things, yes, but you can learn new words by exposure to them.
If somebody now tells me a new word and like the definition of the word, I don't know, some kind of word. If somebody tells that to me now, I have 24 years of experience of knowing what all these other words are.
Yeah, and you associate it with those other words as well.
Yeah, but I mean that's not learning
Okay.
fast.
Okay. All right. I'll tell everything what I mean by that.
Okay.
I mean, there are neural networks, artificial neural systems that do iteration. They use backpropagation.
Like multi-layer
You probably and you have to go through the data set many times over, 1,000 times, 10,000 times. I don't consider that fast.
So most neural nets don't do one-shot learning.
Yeah. In human, one-shot learning takes 5 shots. Or half. Yeah. But in many of these other, it takes 10,000.
And moreover, I think another important distinction is most neural networks, when you do store something new, and you write, you train it many times, you finally get it in there in the network. You've also probably erased other things that are in there, right? There's a bunch of other things that you got previously in there that now you've interfered with potentially, and they're starting to sort of die away. So
having separate processes.
Evan had a question.
Yeah.
There are some networks that do that, though.
Oh, yeah.
I mean,
Oh, yeah.
One shot or dozen shot, and that goes to Lisa's point of you have this separate representation you've learned on millions of images. Sure, it took you a while to learn that, but now if you have some feature basis, so now you see one new image of a type of you've never seen a giraffe before, and then you get the first image of a giraffe. You have that image in that basis you've learned, maybe you can now recognize giraffe, or just a dozen images. You don't need a million images of a new category, as long as you've seen a million images of some set of categories to have a reasonable representation.
If you have a right organization, and in some sense that you actually store things instead of modify everything to learn new things. That's the important thing.
It's not a network that modifies everything, though. There's a network that has a fixed size representation. It's trained by backprop. It's 4,000 dimensions just to work with. And then if you just learn a new category in terms of these dimensions, it then still
that doesn't scale though, right? As you continue to feed in new categories, your ability to recognize or differentiate between all the categories drops. That's right. As you try to increase the number of categories that you're trying to differentiate between.
Maybe I can. Maybe I can resolve this. Just you have to look at how many modified weights are there in a total network, and that gives you some sort of maximum capacity that network can hold.
Sure.
And my thing is that if you have a separate thing, then that can get you out of that bind. You still have with this one. You have lots of modifiable weights. You can't get around that. So randomness. If you look at how much information there is passed to us in our genes, about 3 billion base pairs, and then if you compare that to number of neurons or number of synapses, this is minuscule compared to number of synapses. So the information for wiring up the human being, wiring up the brain, is not sufficient to specify the brain in complete detail. Well, one way is that you can say, okay, you specify a certain part and you say, do 500 of those and 600 of those, and that's sort of engineering solution. Another thing is that you don't actually have to. If you may be able to get by without specifying everything in infinite detail, or if you can actually use randomness as some sort of to benefit from randomness. So you can use random things later on and still build a working system. So having a positive role for randomness is one of the things that I would say is a principle that can be justified on basis of looking at brains and nervous systems. And another thing is that things degrade gracefully. Neurons can die, and this does not mean that certain specific. I knew every word in this world except apple, and because apple just died. grandmother. This is called the grandmother cell. So this can be avoided if the representation is what I've used here, the holographic or holistic, distributed over the whole. And I will show example how that can be done. And it's demonstrated with these 10,000-bit words and vectors. So we're getting slowly getting to the 10,000-bit computing. But let's look at the computing we all know. And that's with words that are, well, up to 64 bits maybe, or 32 bits, whatever it's in your architecture. Okay, in your computer you have what's called the arithmetic logic unit. You have the memory, and the arithmetic logic unit, it has built-in circuits for certain operations like addition and multiplication, and you can compare. So they work for numbers. You can add numbers, you can multiply numbers, you can compare numbers. Then there's a random access memory that stores numbers and it stores pointers, and it also stores the program code, which is basically it's numbers and pointers. And the pointers in modern programming, pointers are really all important because they allow you to deal with things like sets and sequences and lists and trees and tables, matrices, vectors. But in essence, you still have to say pointer is still a number. So the computer that we all have on our laptops or cellular telephones, they really are designed to build with numbers, and they build the program itself. Really, is just in the end, it's manipulation of numbers. For the 10,000-bit computer that I'm here imagining, it would actually be very similar in concept, except that now instead of numbers, the basic unit that you deal with is this very high-dimensional vector. And so now you have to have an addition operator, way of adding these vectors and multiplying these vectors and comparing these vectors. And now I could put the add and multiply in quotes because it's not addition like addition of numbers, but it's an operation that corresponds to addition, an operation that corresponds to multiplication with numbers. With vectors, for binary vectors for addition, we can use a thresholded sum. If we have three vectors, binary vectors A, B, and C, then we add column-wise and then threshold, and then we get a new vector that is a binary. For multiplying, if you use coordinate-wise exclusive OR, which means if two digits are the same, the result is 0. If two are different, the result is 1. I'll show an example. An exclusive OR, it's mathematicians like to call it multiplication, addition modulo 2. And for comparing Hamming distance is, in other words, the number of places at which two bit strings differ. And with these operations, add and multiply, just these two operations, and we can encode and decode information into high-dimensional vectors. Just wait. I'll show. It's an example. Threshold, yeah. And then, as I've already advertised before, the computer also needs a memory, and one possibility is this sparse distributed memory. It's content addressable, and I'll not go into what that exactly means, but it means that if you think of ordinary memory, you give it an address, and it's just whatever is stored in address can be totally unrelated to the address. It's there are two totally different bit strings. One, the address you give, and then what is contained in that location. Content addressable is achieved if the information that is stored in the location is somehow related to the information that's used to address a location. And so this kind of memory is addressed with 10,000-bit words, and it stores 10,000-bit words. And stores 10,000-bit words in the sense that I give it 10,000 bits, somehow it puts it into memory, and later on you can use an address and you get 10,000 bits back. It doesn't mean that it uses a single memory location to store it the way it's done in ordinary computer RAM. And the addresses can be noisy, and here we're using the high dimensionality and various other properties of the memory. And this is also true in hub-field networks. If you come at it with a bit pattern that is similar to something that has been stored, it will retrieve in one or several iterations. It retrieves the pattern that has been stored, and that's what content addressable in essence it means. And the problem with hub-field net is that you cannot make it arbitrarily large. So to make it arbitrarily large, you have to make arbitrarily long bit strings. Not with 10,000 bit words you cannot make it. Whereas sparse distributed memory, you can make it arbitrarily large. So there's enough room there to store a lifetime's worth of information.
So it can be arbitrarily large with 10,000 bits. But is there? I mean, at what point can you make it arbitrary? Like, how many bits
there are
can you
two.
Make it arbitrarily large?
This is hub-field net is a square matrix.
Yeah.
10,000 by 10,000. Here you have 10,000 one direction, and the other you could go all the way 2 to 10,000. I mean, that many possible different variations. Of course, you never need 2 to 10,000 because that's bigger than astronomically large numbers.
So I guess, maybe it's slightly confusing. You're saying it can be made, it's arbitrarily large, but it's actually still finite. It's just a huge number.
It's
2 to the 1.
Enough that you can.
To the number of nodes as opposed to scales.
Yeah. It can be made big enough that you can do 800 books a day. Okay. Yeah, and that's enough for a lifetime. That's actually, yeah. Well, yeah. Well,
a lot of repetitive information and fun nonsense you can throw out.
So now we get to the fun part, and that is, how do you then code information into these 10,000-bit vectors, in general, into high dimension? Here's what every programmer knows. I mean, you have something to encode, like the variable x has value a, variable y has value b. So how do you put that in your computer? You just assign memory, some memory for the variable x, some memory for variable y, some memory for variable z, and then you put the number or whatever value goes into that slot. And so you have these distinct, separate fields for the variables. Another terminologies is variable value, or it could be attribute value or role fillers. So these would be the roles and these would be the fillers. This would be the attribute, this would be the value. Depends where you come from. If you come from mathematics, you don't talk about roles and fillers. If you come from cognitive science, you talk of roles and fillers more than variables and values. But in a distributed representation, we just have these 10,000 bits, and we want to put all of it into 10,000 bits, so that there are no separate disjoint fields. And how would we do that? First of all, for each of these things, we have to have some way of representing each of the variables, each of the values. And now we use the randomness. What I said, we should be able to use randomness to advantage. And here we just say, okay, let's say we just randomly choose 6 10,000-bit vectors, x, y, z, a, b, c, independently, randomly from one another, and then they, from now on, they represent these entities in the system, and in this example. So encoding the thing, you have the variable x and its value. Those were chosen at random with 10,000-bit strings, and now we have to bind these to get the meaning at x equals a, and for that we use the multiplication operation of this system, and this multiplication of operation was this exclusive OR, and so here what we've done here is we have gone like 1 0 gives 1, 0 0 gives 0, 1 1 gives 0, and on the right it's just a copied here for the benefit of what will come soon. So now we have encoded x equals a. We encode y equals b using the same multiplication operator, and then for the third one use the same z equals c. And now the next thing, how do we combine? Now we have each of those individually encoded. How do we combine the three things into a single thing? First we do just plain arithmetic. 1 plus 0 plus 1, that gives 2. And so in this column there were 2 1s, this way it had 3 1s, this one column had 1 and that is 0. So that's an intermediate. And now we do the thresholding. The threshold is we use the half the number. In this case we have 3, so we do the threshold at 1.5, and anything that's above 1.5 becomes 1, and everything is below it becomes 0. So now we have a representation, binary string representation for this entire record, and that's the capital H. And so far so good. But now the interesting thing is that in this compound vector, can we still identify what went into it? Can we say that, oh yeah, in this thing, can we extract what the value of x was? Because if we go into traditional representation, okay, we have a record with 3 fields, and if we want to know what the value of x is in that 3-field record, we just okay, x is the first of those fields. We just pull it out. Now we don't have that option here, but we have some other way of doing it, and we again use the operator. Okay, first of all, before I go to the next slide, I want to show you we have had 3 multiply operations in this sense of multiply, and we have had 1 addition operator in this sense. And so these the question is how do we extract the value of x from it? And so here's the compound record, and then this is the x, same thing as was in it. And there again we use an operation that I've already introduced, and that is the multiplication. It turns out that we need to multiply with the inverse of x, but this being binary and the exclusive OR being the operation, the inverse is itself. And so this multiplication operator gives us something. It's not exactly the right answer, but it is close enough so that in a high-dimensional space we can identify the approximate answer with the exact one. And so if we have kept track of everything, we have this kind of associative memory that has everything stored in it that has been introduced into the system so far. Then, and we search that memory for the best match, then it turns out actually that this approximate result finds, with very high probability finds the correct answer as the best match. So just a review slide, and just what is the underlying mathematics that makes it work. If you mathematically inclined, this may be sort of very, very simple. First of all, a randomly chosen vector is dissimilar or nearly orthogonal to anything that is being chosen so far, or seen so far. Then addition operator, this thresholded sum, it produces a result that is similar to what went into the sum. So if we had three vectors in a sum, the result the thresholded result is similar to each of those three. But the multiplication, the exclusive OR, it produces a vector that is dissimilar to what are being multiplied. And the thing that one set be similar and the other be dissimilar is actually very important for this mathematics to work. And then if you start looking at this in abstract algebra terms, the important thing is that the addition operator and the multiplication operator they constitute an algebraic field over the vectors. And this is true for numbers. I mean, the numbers with addition and multiplication, they are a field in abstract algebra terms. And so here we have just other kinds of entities. We have these high-dimensional vectors, and we have something that is a field. Actually, it is approximately a field. It's not exactly, but that's good enough. And when you're dealing with fields, you get some things like inverses and distributivity, and all of these actually worked in that example, although I'm not going into the details. Yes.
What does it mean that it's approximately a field?
The addition operator in a field, the addition operator should be associative. Here it isn't, because if you if you are getting the thresholded sum of two binary vectors, you get ties. I mean, and so all the axioms, field axioms, do not hold exactly, but they hold approximately. I would say that's, and so what you can get out of fields, you can get out of this kind of thing because of the high dimensionality. Another thing, multiplication preserves distance. That played a role in this example. And then, of course, the important thing is that it's possible to have an associative memory that can be arbitrarily large to hold results that have been computed so far. And that's very much the way we have in ordinary computer memory. We compute a few things with the operations we have, and then we put them in memory and can later use those. So in that sense, there's a lot of similarity. There's a lot of similarity to how computers work. Yeah.
Earlier, when you were mentioning that the addresses themselves can be noisy,
yeah.
Is that what you're referring to here when you're saying that you take H and
yeah.
you when you multiply it by X, X
yeah.
can still be noisy. It doesn't have to be the same original X. And you can still get back A.
You could still, yeah.
Okay.
But yeah. And the thing that the multiplication preserves distance, however much noise there is in the X that you use, that also will then be, if that much more noise, it will be added to the approximate A.
Oh, okay.
Just now you can save the whole expression in only one 10,000-bit unit.
Yes.
But for retrieve the information, you need to save each of the concepts.
You have to have stored. Yeah, you have to have stored. Your storage. Let me. Can I go back? This storage has to include. It has to include each one of these.
So we need 6 units of 10,000 bits.
Yeah.
Does that take too much space?
No.
One unit for the whole expression, but you need 6 units to help this expression work.
At any one time, you are only dealing. You're still dealing with that one 10,000-bit entity, and then you use operations in your arithmetic logic unit to compute other entities that are again 10,000 bits. So how would I say? The important thing is that everything, being at the variable, being at value, being at this composite thing, everything actually is represented as a 10,000-bit entity. And so if you have operators that work with 10,000-bit entities, then you can combine those with the operators and get new entities. Yeah.
And this retrieval process is kind of limited to certain types of questions, in a sense, because
Yeah.
here you have to say something was bound with X
Yeah.
in H. What was it?
Yes.
But you can't say arbitrarily, actually, so it's kind of like I have two concepts that were tied together, but one of them I forget,
Yeah.
something like that. But you can't, basically you have to kind of know the structure of the input to extract the pieces.
I have done this in a very traditional way, you're right, in that I've just taken what we usually do in ordinary computing, have variables and values, and I've just it can be encoded.
What if X was not contained in H, and then you asked?
You'd get you would get something for which there's nothing equivalent in here. Okay, that's another. Yeah, that's another important property of these associative memories. Not only can you find if there's a best match if it is close enough. If there's nothing that has been stored, anything like that, you get an answer from the memory, I don't know. In other words, some sort of probability, and it again comes from the high-dimensional representation.
But I guess the thing is, like, what you would get back is just it wouldn't match anything else that exists because the probability that would happen by accident.
It would still be closest to something, but it would be so far from that something that the feedback that you get from memory would say, no.
Okay.
Yeah.
So you could probe at random until you got something you recognized.
Yeah.
And you're like, all right, this is what's going on.
You can put a lot of random things before you find something that is close. That's the nice thing about it. Shall I go ahead? Okay, that's the math. Okay, I guess that's the most mathematical part of my talk. And the thing is that high dimensionality really is the key. Because if you think of 10,000 dimensional space and being a binary space or being real numbers or whatever, you really have only 10,000 that is mutually orthogonal vectors. And every engineer knows that mutually orthogonal vectors are nice because and you can keep things apart. But with high dimensions, you have billions of nearly orthogonal vectors, and if you can tolerate that, then this randomness produces you nearly orthogonal. You get nearly orthogonal vectors nearly free, and that's a very important thing to have in an architecture. And if you choose randomly vector, it is nearly orthogonal to anything that the system has ever seen so far. And I just like this picture. It took me a lot of time to make this picture, so I show it Troy. Half a day work. Now, representation is very important for computing, and you probably don't usually think about it, but in these computers, I mean, if you're not a programmer, you probably don't think about it. But the numbers are represented in binary, and it turns out that circuits for binary addition and multiplication are fairly simple. And so binary representation is very convenient for ordinary arithmetic. And now I'm trying to, in an example, show how if you use this high-dimensional representation, you do some other things very simply. And my example is mining for meaning, taking text and finding word meanings. Some people here may have heard about semantic vectors or context vectors. My example is about the semantic vectors. It's synonyms. My example is about semantic vectors. And semantic vector is something we have words, and if you take just words, the letter string in itself has no meaning, but after we have encountered words in many contexts, the word begins to have a meaning for us. And this is what I mean by semantic vectors, the meaning. In other words, there would be some representation of a word such that if two words have similar meaning, their semantic vectors would be close in a space, and if they have dissimilar meaning, then they would be sort of orthogonal to each other in this space. And so each word is represented by 10,000 dimensional vector. And they are learned by reading text. And we want this idea that then the semantic vectors for word obey this. Similar meanings would acquire similar vectors, dissimilar with dissimilar. And there's probably one of the better known, certainly in linguistic circles, is latent semantic analysis, latent semantic indexing. It uses singular value decomposition, which is one form of principal components, really. And so it produces semantic vectors using principal components. It reconstructs semantic vectors from. So that principal components analysis actually is pretty heavy duty, and you have to first collect the statistics, and then you do this heavy duty thing. And random indexing actually doesn't require that, so it is much simpler, and it is based. The idea is based on random projections. People who work with large data, if they don't buy the day, if they don't know random projections, they sort of are behind times. So, but random. Okay, what is it about random projections? It is one of those things that somewhat counterintuitive. So it's a little bit like magic, but once you get it working for you, you sort of begin to accept it and understand it, and so that's what my example is random indexing based on random projections. So we have tremendous amount of text, and somebody right now, as we're sitting here, somebody is entering more text into the internet, so we'll never run out of text to analyze. So there's our data, and each word in a text, the different words, they constitute the vocabulary. I mean, by vocabulary, if you take all the web page, all the Wikipedia pages, its vocabulary is all the different words that appear in Wikipedia. And for this algorithm, each of those words will be represented by two 10,000-bit words. One is a random label, and the other is a semantic vector. That's what the algorithm produces. It produces semantic vectors using random labels as intermediaries. And a random vector, the random label, it is as suggested by the name. It is chosen at random. First time you encounter the text, when you go through your data set, and then that stays fixed through the rest of the algorithm. And because of the dimensionality, it would be very dissimilar or uncorrelated with all the other labels that have been used in the system. And then the semantic vector is learned from the data with the help of the labels. To explain the algorithm, we have to see how the text is processed using these random labels. And each word in the text, in turn, becomes the focus word. So you have these millions or billions of words of text. There's just one word at a time, and so you go through the text, and each word in turn becomes the focus word, and so now you're looking at that. And the words around it, for example, 3 words before and 3 words after, are that word's context at that location. Could be the context window. And here's my example. You in a text you may have this: the quick brown fox jumped over the lazy dog's back, and you've just gone through, and then you're finally at the word over. So that's your focus. The 3 words before and the 3 words after are the context window, and so the current context for the word over. And while we are here, this is the total algorithm. You start with all semantic vectors with 0 because you really don't know anything. You step through the text one word at a time. That's indicated here. Then you update the semantic vector for the focus word with the random labels for the context words. And that's all there's to it. That's a little bit more engineering to it. I mean, things in linguists, they like to leave very frequent words out of this because they really don't contribute. They call them function words. So sometimes you can also convert the words into their basic form. So instead of jump, use a jump and dogs. But those are details. But the principle of the algorithm is that you go through the text and you update the context vectors as for each word as you go through.
So using the addition you described before.
You can use the. Here I would say you do not. You use just an ordinary vector addition. In other words, you will not go into binary.
Yeah.
At this point. You just. It's a vector sum. It's a vector sum.
Oh, so these are the analog numbers now.
Yeah. Right. And actually, if you want to go more into the details, it turns out the best random labels are that they have very small. I mean, out of the 10,000 dimensions, you may have 15 ones, 15 minus ones, and the rest of them are zeros. Very sparse, but equal number of zeros and ones, and that way you always hover around 0 as the mean, and it means that the dynamic range doesn't even need to be more. And if you have overflows or underflows, you lose very little information. So that's part of the technology.
So when you update the semantic vector for the focus word you use the semantic vector of that word. Do you use the label for that word?
Labels never change.
But you use the label.
But you use the labels.
And you put the labels of the surrounding words on either side of it.
Yeah, you add them into the semantic vector.
You just add them to that.
You just do simple addition.
You put them in juxtaposed front and back.
Yeah.
You just add them.
Add them as vectors. Yeah, and so you end up. Yeah, it's again seems funny, but that's how we learn to understand words in our own language. Somehow we just hear words, and once we hear enough, somehow words become related to one another, and we can retrieve. The concept gets formed, but also from the concept we can retrieve the words. So there's something. I feel in this there's something very, very similar to how we come to deal with words in truncate. What would you truncate?
Adding them, is it
10,000. You don't.
Is it XOR?
The vector. Everything stays in 10,000 dimensions.
Okay, but do you truncate when you
No. This is that would be a straight vector sum.
Okay.
Yeah, and it could be compared with cosine. The results could be compared with cosine. Yeah, and if the cosine is and it produces semantic vectors that have the required properties. Linguists have this phrase that words become to be known by the company they keep, and this actually is a very nice way to model that. If you realize, I mentioned latent semantic analysis that requires singular value decomposition. This one doesn't need it incrementally. At any point, you can stop the process, and you have a perfectly usable semantic vector. And when new vocabulary words occur, you just produce a new random label, and you can go on. And it's scalable because the dimensionality of the vectors doesn't have to increase with the increase in vocabulary. And actually, the random indexing can be done in two dimensions. so that even if the vocabulary grows, your table for storing this information doesn't have to grow. Another thing, it can be made to include things like word order, which is sort of beginnings of grammar. English certainly uses word order to express grammar. And the algorithm is actually much more general than what its applicability is much more general than just language and context words. Anything where you have sparse, irregular, dynamic change in big data, this could be a social networks, that kinds of things, where nodes come and others go. This algorithm works well so long as you have a lot of data. And the thing is, when the random labels are sort of zero mean, things that disappear, they eventually also disappear from the thing because they just get overwritten by in the sum. They get overwritten by other things. So things. And this kind of algorithm actually is already practical on today's computers. It is being used. I don't know if Google uses it for their search engines, but they could, and someday they will. I had a little bit about representing sequences, but I will not go through those details. I've written a paper about this, and I think it'll be available.
Yeah, put them on the wiki.
Yeah, and it is just as good as what I would say here, because I want to leave a little bit of time for discussion. But I just say enough that, okay, if you think of a set mathematically, the order of the elements doesn't matter. And so the thresholded sum, in how you produce a sum, the order of the things doesn't matter. So that's a very nice thing. Thresholded sum is a very nice thing for representing sets. Doesn't matter in which. But sequences, the order does matter. And so now you have to have some way of representing it in a sequence A, B, C, that A was the first and then B and C. And I'll just go show the very... It can be done by using permutations. And each element in the sequence is taken, but the previous, whatever that element's history is, it is first permuted. So when we see A, well, that's all there is. When we see B, its history is A, but we permute the A, as a random permutation will do, and then we add that to B. And then we get C, where we permute what the history of C is, and when we get D, we permute all the... And then again, permutation, it distributes over addition, so this can be written as, so there's when we have C, A, B, C, D, the sum includes D, it includes C, but it has been permuted once, it includes B, but it has been permuted twice, it includes A, permuted 3 times, and in some sense the permutations keep track of how far in the sequence a thing occurred, and it means then that the order will be, I mean, same things that occur in different order will be encoded with different vectors, and this can be decoded using the inverse permutation. Another thing about permutation: for every permutation, there's an inverse. And so you can actually recover it, but I'll not go through that, because there's something more, a few more things to be said, and that's about the pointers. If you think of ordinary symbolic programming, symbolic artificial intelligence, it's really computing with pointers. Lisp really is a programming language for dealing with pointers. And pointers let you express very complicated expressions, and in some sense a Lisp pointer represents everything that it points to. And in that sense, that pointer represents a big amount of information. But it's still an address to memory, and if you have 2 pointers that differ by simply 1 bit, you cannot tell anything about the meaning of those things. Now here we will have 10,000-bit pointers. Not only that, the pointers actually are made from data. And so we have a totally new kind of thing to be introduced into computing, and that is pointers that encode information. And they are possible if we have memory that stores 10,000-bit patterns and can be addressed with 10,000-bit patterns. And that's with the content addressable memory. And if you think of the amount of information at one of these pointers, it's sort of equivalent to page of text. So you really have something totally new that computer science hasn't considered before, and we're we can begin to think in terms of computing with pointers that are actually informative. Another thing is that these 10,000-bit words also can be words that used as mappings. And when we use the variable, it's called variable binding. We combine the variable with its value. We use the multiplication. In some sense, we mapped that pair into different part of the space. But these kinds of mappings can be also learned from examples. And this is a possible mechanism for figurative use of language. If you look at this sentence, what is $1 in Mexico? There is no such thing, and yet we understand. And I'd say most of us have a ready question, and we probably agree what the ready answer, and we probably agree what the answer is. And so in this case, we use $1 as a variable. But if you take ordinary computer programming, there is no clear way where you could use you could use what is in one case a value, use it as a variable. So because of the mapping property, we can do other kinds of computations that are not part of our current computing repertoire. So there's something to be studied and learned and understood in how you compute with these high-dimensional vectors, and so then the thing is, will this actually matter? And I think it will. And the thing is that technology is catching up with these ideas. And the thing is, what's called nanotechnology, it will be able to produce circuits that are commensurate in size by the human brain, or even a cat brain, and that use very little space and use very little energy. And this is what makes this kind of theorizing actually something that is worth pursuing also as a practical enterprise, so that when the engineers are ready for us, we would be ready for them with our theories. So I have just put here some names. This kind of work this theorizing has been going on for over 20 years, and if you if you want to search the internet, here are some names and search words, and I think the paper contains all these names. So that is with the thank you to all of you, and I can stay here for a while to talk. I think that officially time is up, and I'm usually here on Fridays, so we can continue discussions. And if you have questions about the paper that Bruno put in there, just drop me a line. So thank you very much.
Okay,
So I guess we let people go, and those who stay
Sure,
can
we
stay.
Stick around and ask questions.
Yeah.
That's the paper.
That's the paper, the matrix binding of additive. Yeah. I came across it as a reference in a paper I was reviewing, and I was like, what? I've never heard of this kind of thing before. And then here to see it again is very surprising.
Permutation, but it's a random permutation. How can you do the inverse?
It's just
Yeah, I think well, the
any
I had looked at
any permutation. If you have
trying to really
any permutation has an inverse.
Yeah, you mean we need to store the permutation?
Oh yes,
That's true.
that's
If A is permuted randomly, it is also quite. It is also should be orthogonal to A, right?
You're right. Yeah, and successive permutations are just again permutations. It's a different. Each one is different. So that makes
You need to store.
You have to have. You only need to store one permutation matrix and its inverse.
Okay.
Because you use the same permutation.
You use the
successive.
Okay.
Yeah. So it's
yeah, that makes sense.
Yeah.
You mentioned that this is practical in today's computer.
Yeah, this random indexing.
Yeah.
Random indexing.
How is this done? How efficient is this actually? Is it can you store big amounts of data? And
My experiment was, I think it was a year, maybe 10 million words and vocabulary of 30,000, and it would run in 10 minutes when the singular value decomposition would take several hours.
Okay. So it's
and the bigger the vocabulary gets, the more this wins.
Okay.
Yeah, because it goes linearly.
Yeah. Also, it serves the whole space.
It still any of these problems have to go through every word, one word at a time.
When you want to find the closest match, you need actually to check every.
That's true. Yeah, and I didn't go into the practicalities of that.
You have to check. You have to check with all the rest of them until you come to the one.
Yeah.
I mean, as soon as you come to the one, you're done. So it's or the end of the two.
But it's so for high performance, it is still not so good.
I think it's only if it's very, very large. But I would say random indexing, random projection in general, I think it's very useful on Computation. Very useful.
Because it can provide what you said here, and it's amazing.
Yeah, no, it sort of takes people by surprise.
Yeah, it is.
It's subtle. It's subtle, and it is high dimensionality is important here because things don't really to get any reliability in these algorithms.
Why exactly 10,000? Maybe you.
I like the number, and I know 500 isn't enough. And 10,000 is doable in today's computer.
On average,
yeah, and you don't need 100,000. That's the other thing. You don't need to go. Yeah, I think you can handle the whole world's population. Who talks to whom network with maybe 100,000. There's 100,000. Because the information is so sparse.
But the problem is, like you said, there's a lot of
really, there are lots of people in this world, but any one person communicates. There are lots of words in this world,
if you don't know, if you have some sort of
only very few are together.
It's sparse.
This is because it's sparse. So this is a way to
randomly. I guess it's randomly concept you know.
Yeah, it was very interesting.
But you don't know if it's made in that construct, and it gives you back to this nothing like you know, and it wasn't in there originally.
Okay, so
assuming that it was made up of the
these
concepts
2
you
points
use.
on the hypercube, and you have a path.
Basically,
and you say, and then you have 2 other points, and you have another path.
Yeah.
And you're saying those paths are close together.
No, because usually the way
It's not, well,
What was that the distance between two paths, and how do you measure that?
Trying to think of someone's name, right?
Maybe
you made hanging distance between the vectors themselves.
Yeah, okay, you have a hanging distance between these two
Well,
vectors.
that's the length of the path. That is the length of the path. The shortest path is the hanging distance. You don't compare.
Okay. So I thought you were comparing one path to another path. So what's the bell-shaped
When I
curve
first
then?
looked at the paper,
All the paths are about the same length?
I was like,
The bell-shaped curve
inspired by it, but now
is the binomial distribution.
It's this whole, this all
And it tells
it's a whole community.
if
What's fascinating about it
if
is
you
like
take
they've
any
all come
corner in the hybrid
somewhat independently,
and then measure
and really
how many points in the hybrid you get. One step away,
just
two
don't have
steps away, 3 steps away.
neural network and traditional neural network.
yeah, it's very
Because these are all
So, this is steps.
It's sort of deceiving because it seems almost too simple. Like if you add together vectors, and then you take the dot product of that. Basically, this is like my understanding of one of the main properties. Is you add together some vectors. If you take the dot product of one of those vectors that you had put into the sum,
Yeah, and then when you go 1, 2, 3, 4,
positive.
then you get here
Any like other vectors will be negative.
5,000 or
So I
10,000.
guess then there has to be some. I
Everybody
guess
is
that's where the
there.
high dimensional
So,
helps you
so
even more.
almost everybody
The ones that
has
aren't in there will be less likely to
5,000
be
degrees
that
of
positive,
separation.
Yes.
strong positive
Yes.
output
Yes.
of the dot product.
Yes, that's it.
That's weird.
That's it.
Otherwise,
That's
you're
it.
gonna-
That's it.
Yeah, otherwise,
That we don't have
property
our
doesn't hold
intuition is
forever.
for that.
At some point, you can randomly program
Well, that's high dimension. That comes from counting. You can count.
No, I know. I mean, I believe you.
Yeah. No, it's things like.
You have to go to another meeting right
Oh,
now, but
okay.
in my office.
And
But
I
anyways,
need to
but
go.
thanks so much.
Well,
This is awesome.
You're
Yeah.
welcome. I think it went well. Yeah, people stayed. I think
Yeah.
that's a test.
Yeah. Okay.
Okay, I think we'll.
This goes in my ear. Yeah.
Oh.
Okay, I have to give this to Mayur. Yeah, I have the meeting right now. What? Oh, I'm so yeah. Now it should be my office hours, but I'm sort of still incognito this week.
yeah.
But anyways, we can some other tomorrow, whenever. Next.
Tomorrow.
Okay.
I just want to present my idea.
Yeah, sure. It sounds like a great idea. I mean, in general, something about it. I mean, sounds.